And we talk about the Yang-Baxter representations of the infinite symmetric.
Yeah, thanks, Roberto. Thanks to the organizers for having me here. It's a pleasure. And well, I will talk about joint work with Ulrich Pennig and Simon Wood, all from Cardiff, on something again related to Yang-Baxter, to the Yang-Baxter equation. We've seen it in quite a few talks already. It's one of these wonderful equations that appears everywhere. Yeah? So Yang and Baxter, well, they know it from quantum mechanics and quantum statistical mechanics. I prefer to see it in the context of integral quantum field theory, but it appears in knot theory, it appears in subfactors and quantum groups. So most of you should have a reason to be interested in it, I hope. Although I will concentrate on a very simple kind of Yang-Baxter equation. We already heard in the last talk there, well, it's not just one Yang-Baxter equation, but, well, different variation exists, and then I will make perfectly clear which one I'm talking about. Yeah, it's my plan to keep this very accessible, so I want to start out simple. Yeah? So here I've drawn for you all the integers, or at least a few of them. Yeah? And you can think of it as a spin chain if you're a physicist, but I should tell you from the beginning there are no periodic boundary conditions. In fact, the beginning of the chain is most important to us, yeah? And it's certainly not periodic at all. And in the end, I want to talk about an infinitely long chain, all integers. Yeah? So the title contains symmetric groups, permutations. So let me introduce some very basic notation. So the permutation, the two-cycle exchanging the first two elements, I call sigma 1. You've seen that before, right? And then there's sigma 2 and 3 and so on. Yeah, so all these exchanges of nearest neighbors. And we all know the equations that you have in symmetric groups. Say if you look at the first three and you first swap the first pair, then the second and the first, you could also first swap the second pair, then the first and the second. That's expressed here. It's one of the important equations in the symmetric group. If you swap twice, you get the identity. And if these generators are sufficiently far away from each other, they don't interfere, they commute. Yeah? So these are the defining relations of the symmetric group. And I don't put a constraint here on the number of generators, so it's the infinite symmetric group, right? And I always view it as a kind of inductive limit. So if I should ever talk about a finite symmetric group, I mean it to act on the first couple elements. Yeah? So S3 only permutes the first three and keeps the rest fixed. Yeah? S4 and so on. Yeah? S infinity, in the end, are all permutations of the integers, keeping basically everything fixed except for finitely many points. Yeah? So that's S infinity. It looks innocent, but it is wild. Yeah? So it's not a type 1 group. It has, its irreducible representations are not really classifiable. It has many unitary type 2 representation. It's called wild, but quite a few things are known about it. And also in our Yang-Baxter business, we will make contact with it. Okay, so far for permutations. Now Yang-Baxter, well, we've seen that many times. Every integer gets replaced by a vector space copy. Let's keep it finite for the time being. So let's say really 7. Yeah. So I take 7 times the same vector space, always tensor products. And I now implement these symmetries on that tensor product by picking some element in the endomorphism of the tensor square, so something that works on just 2 elements, and introduce standard notation. So R1 is the operator that acts as R on the first 2 copies and trivially on the rest. You can guess R2 acts on the second 2, trivially on the first and trivially on the rest, and so on. These are your operators. And then the Yang-Baxter equation in my context very simply says R1 times R2 times R1 is the same as R2 times R1 times R2. Yeah. So that was, in the last talk, the point was made this would not be the Yang-Baxter equation because it lacks a spectral parameter. Well, up to you, I guess, if you call it Yang-Baxter or not. So in case you have a spectral parameter, you can put it back into this form without spectral parameter, but on an infinite dimensional space. So that's one way to view it. Or you could say, well, I take such a solution and then I try to Baxterize and put in the parameter. For this talk, there won't be any spectral parameter. Okay, so we all draw pictures here. So in pictorial language, that is the Yang-Baxter equation. You first act left, then right, then left, or the other way around. That should give you the same. Yeah? And to make a concise definition, I emphasize this definition is only for the purpose of this talk, otherwise it would probably be controversial. So what I fix here is a finite dimensional Hilbert space, so there's also a scalar product. And I say an R matrix, well, that's something on 2 copies. It's a unitary on 2, which satisfies Yang-Baxter and moreover squares to the identity. So I ask a lot. Yeah? I would like to drop that, obviously. Then I would be talking about braid group representations instead. For now, we keep it. I should say, in the context of integrable quantum field theory, that is what you typically have for your 2-body scattering matrix, if you also have a spectral parameter. But you factor through the symmetric group in that case. That's why I'm interested in that situation. Or you could say, I look at such a 2-body scattering matrix at 0 momentum transfer. That's such a gadget as well. Yeah. All right. Before I carry on, I should convince you that there exist at least a few examples, because I ask really very much. Yeah? Let me write down very simple examples. You could take the identity, right? That works. You could take minus the identity. That also works. Or you could take, well, almost as simple, the flip. The flip will always denote, if I have a tensor product of 2 vector spaces, well, you just flip it, right? That also works. Or you could take minus that. And then maybe you have to start thinking, yeah? What are all the other solutions? And there are infinitely many more. Yeah? Okay, but we will see these along the talk many times. Good. I will call R0 the set of all such R matrices with any V. Yeah? So just union over all finite dimensional vector spaces of these solutions. So if you are an old school quantum field theory guy, that looks like a von Neumann algebra, yeah? A ring. And well, it's not a ring, but it's almost a ring, I will tell you. Yeah? So it's almost a ring, what you get. And this 0 is only meant to indicate that we have this additional square is equal to 1 condition. It's an involution, and because some things that we do work also without the 0. Yeah? Okay, so that much for that. As I already told you, such an R matrix gives representations of symmetric groups. So you pick now any such R, and what you get is, well, first of all, let's say finite representations, which I call rho R n of the symmetric group of n letters on the n-fold tensor product. Well, simply you take the generators to these Ri's. Yeah? So that's what you have. And you can also go to the infinite symmetric group. For that, you would need to talk about what you mean by the infinite tensor product, right? So on the level of the Hilbert spaces, I want to avoid that for the time being, because you have to make a choice how to define that. On the level of the endomorphisms, that is easier, because you can just always put the identity. Yeah? And I just mean a algebraic infinite tensor product here for the time being. We will close it to von Neumann algebra later on, but for the time being, just algebraic. So any R matrix gives you homomorphism from, say, the group algebra of the infinite symmetric group into this infinite tensor product. Yeah? And that's one way to study these. Yeah? Okay, so I basically want to compute all solutions, but I want to compute all solutions up to a certain equivalence. And this equivalence comes from quantum field theory, and I guess it's natural enough also in a mathematical context. So let me introduce what this equivalence is. So it's motivated from joint work with Sabina Al-Azavi last year, but the definition is very simple. Take 2 R matrices. They're called equivalent, and I write it with such a little twiddle here. If for each n, their Sn representations are equivalent. So that's the definition. Let me make a simple observation, very simple indeed. So if you have two equivalent R matrices, well, they certainly need to have the same dimension. Dimension of R means dimension of the base space V. Yeah? And if you say you look at n equal 2, so you just look at the 2 cycle and, well, you compute the character, so that's a trace. They need to have the same trace. Yeah? Okay. There's a question.
It's a bit of a weird definition. Would it make sense to also impose the condition that the isomorphism restrict to, I mean, it's a
sounds a bit stronger at the moment. Yeah, at the I'm not asking for any compatibility at the moment between the different intertwiners you would have. You could make variations of it. This turns out to, well, it's very natural in terms of characters, as we will see. Yeah? But you're right, one could talk about directly about the infinite representation. We talk about well, you see, maybe it comes from quantum fields. You think of Fock spaces, yeah? So it should hold for each particle number. That's what we ask here. Yeah? But so let me talk a little bit about this here. So our R matrices are unitary and involutive, so they only have eigenvalues plus minus 1. Yeah? So if you know the dimension and the trace, well, you know the multiplicities. Yeah? So you know them up to unitary equivalence. But you have to worry that when you take an R matrix and you conjugate it with a unitary, typically it won't be a solution anymore of the Yang-Baxter equation. Yeah, so it's not so clear if the other direction holds. There is an old conjecture by Gurevich, actually, to the effect that this is an equivalence. But it's not the case, yeah, as we will see. Yeah, so that equivalence is much stronger than just asking for dimension and trace, as I will explain. Okay, two very simple examples of equivalences. Take any R matrix and sandwich it with an invertible tensor square. Easy enough to check that is equivalent. Or here sandwich it with this flip operator. Also that works. Yeah? But that is not all. Yeah? So that does not exhaust the full equivalence class. Yeah? So that is not everything. Okay. So now we know the definitions, and I will now talk about the questions I'm asking. So I ask 3 questions. First question is, find all R matrices up to equivalence. So I mean really any vector space, yeah? So independent of that. And more concretely, I would like to have a concrete parameterization of this quotient here, so where I divide out the equivalence relation. And let's say for each class a representative, yeah? So a normal form. So that is a very strong way of saying find all solutions. Yeah? That's something we want to do. And second question, given two R matrices, when are they equivalent? Yeah? So you could say, of course, well, I just go to the definition, I compute the representations, break it down into irreducibles, compare multiplicities. That is not what I call efficient. Yeah? So there will be a much, much shorter answer to this. Yeah? That is the second question. And the last question, the third question, is if you just talk about representations of the infinite symmetric group, you could wonder which representations are of Yang-Baxter form, that is, of this form rho R for some R matrix. So these are the questions, and the rest of the talk is about the answers, right? But I hope the questions are at least perfectly clear. They require different tools to answer them. It was a bit surprising. So the Yang-Baxter equation, it looks finite dimensional matrix equation. But to answer is you want to look at von Neumann algebras and subfactors and take some limits and unit topology and all kinds of things. That's at least the way how we solve that. And yeah, so that's why I think it should fit into the subject of this conference. All right, so that's our setting. And now let me start to answer these questions. First, if you think of finite groups, it's a good idea to look at characters, right? And now I produce some characters also here. That is also very helpful in this context. So I will talk about Yang-Baxter characters on the infinite symmetric group. A standard tool is the normalized trace. We've seen it in Stefan's talk yesterday, so it's a very simple thing. You just take the trace on your base space V, divided by the dimension, and you take the same thing in every tensor copy. Yeah? That is standard to call it tau, and also I call it tau here. Yeah? Okay, so that's our normalized trace. And now if you have some R matrix, well, what you form is you go into the representation I described and then take this trace. So that's a function from the group to just numbers, and it's a character. Yeah? a normalized character, I should say. So because this is infinite dimensional, it's a good idea to normalize. So the identity doesn't give you the dimension, but it's normalized to 1 at the identity. Yeah? So it's a normalized character. It forgets about the dimension.
By character, you just mean class function?
Yeah, I will make this very precise. I mean positive normalized class function. Yeah? And it's probably the best way to state it like that. Yeah? So a normalized character, I really mean the same thing as a tracial state on the group algebra. So as I said, tracial, well, I should maybe write it down. Yeah, so to be absolutely clear. So this looks a bit more as if I was thinking about the algebra, but that is what I want. Yeah, so it's tracial. It's normalized at the identity, and well, X now means any element in the group algebra, so that should be positive too. Yeah? So it's a tracial state on this group C-star algebra. So that's what we get for any R matrix, and we want to use it now. Yeah? We want to extract information from it. Let's see. First, you calculate it on an n cycle. So I won't need much information about symmetric groups, but you remember cycles are important. Yeah? So every time you have a permutation, you can write it as a disjoint cycle. So if you have an n cycle, well, let's say you just take this guy. The last one goes to the front, and all the other ones like that. Yeah, that's what when I write Cn, I usually mean this n cycle. This n cycle. So you you have to take the trace over n tensor factors and normalize. Well, that's it, right? So to be equivalent means to have the same dimension and the same character. Yeah? But given two R matrices to compute these characters, it's a bit of a mess. Yeah? Because you have these iterated. I mean, there are many tensor products hidden in the short notation. Yeah? Okay, so that is one thing, and that just tells you it is a tracial state, but it has an additional extra property. Namely, if you take two permutations that have disjoint supports, as support just meaning complement of fixed points, yeah, when you view it as maps from n to n, then it factorizes. Yeah? So it carries a product of two such permutations to a product of character values. That's a special property. Not every character does that. Yeah? That is very special, and we have to keep that in mind. Yeah? Okay, so now we know what we can get from an R matrix, and we have to compare with what's already known on S infinity, generally speaking, and the characters of that. I told you S infinity is wide, so it's not type 1. So to classify irreducible representation is maybe not a good idea, but you can classify extremal characters. And that's old story and well known, but I should recall it here. So that is due to Thoma in the 60s. Following theorem. You just take any character, I always mean a normalized character, of S infinity. That's extremal. So extremal just means you can't write it as a non-trivial convex combination of two others. Yeah? If and only if it has this factorization property I just gave you. In other words, any R matrix gives us an extremal character. Yeah? And much more is true. Thoma has a parameterization for all extremal characters. There are very many. Yeah? You need countably many parameters, but you can do it. So it's a wonderful theorem. And I should write that down here because we will refer to it every now and then. So this big T is the Thoma simplex. And it consists of sequences, alpha and beta, of non-negative real numbers that are ordered. Ordered is just because they should be unique. Yeah? Same for the betas. And you can sum them up. And when you sum them up, you get at most 1. Yeah? So this is a one-to-one parameterization of all extremal traces. And how it works is given by this formula. On an n cycle, you have to look at n-fold powers and sum them up with this little sign for the betas here. Yeah? This is for cycle length at least 2, as a trivial element gets 1, of course. Yeah? Okay, so that is Thoma's story. What we now know, any R matrix gives us such two sequences because it does define an extremal trace, right? The question is which one. Yeah? And the equations you want to solve is here. That's the value a Yang-Baxter character takes on an n cycle. That's Thomas' formula. And the question is compute alpha and beta from that system of equations. And it looks a bit messy at the first sight. Yeah? But again, let me point you out simple examples. So if I have R being the identity, maybe I erase the minus for the time being. Well, then the character is trivial. I don't have any sign, so I just take alpha 1 to be 1, and that's it. All the rest is 0. Yeah? So this gives alpha 1 is 1. Okay, if R is minus the identity, you can easily check all I need is beta 1 is 1, and all the rest must be 0, because the sum of all parameters can be at most 1. Yeah? And if you work a little more, just a little, if you take R to be the flip, well, then you find you have D values, namely alpha 1 to alpha D, and they are all 1 over D, where D is the dimension. Yeah? Just as examples. Yeah? But in general, it seems hard. Yeah? And moreover, you are not so sure which alpha beta values can you actually realize by an R-matrix. So one important question is which Thoma parameters are realized by Yang-Baxter characters. Yeah? So I will have a subset in this Thoma simplex, which I call Thoma Yang-Baxter, that consists of all the parameters parameterizing Yang-Baxter characters. And it's not the whole story. Yeah? It's really a subset. Yeah? Yes?
So you define a character here starting from a representation.
Not necessarily. In our case, you mean, yes.
Yes.
Mm-hmm.
So what is it? So because here, if you have, for example, a finite dimensional representation of a group, just to take the trace, or so what is your
So here, maybe to repeat that. So in this context, it's a positive normalized class function. That's the definition of character. It's the same as for finite groups, just normalized. Yeah.
Yeah. So. Okay.
Yeah. And then you, in addition, ask extremal. Yeah? So it means you get a factor if you go to the Von-Neumann algebra in the representation. And these can be classified. Yeah? That's the content of this theorem. Yeah?
So you look at the group algebra.
In the representation, not just the group algebra. Yeah?
In the
so I will do that. Yeah? All right. So these are the questions. Which Thoma parameters are realized in Yang-Baxter form. And one first, so I will now deduce extra information of these parameters coming from R-matrices, yeah? Because they have specific properties that go beyond the generic properties of any extremal character. Yeah? And one first observation is that the Yang-Baxter representation is very small. Small in a certain sense. I mean, it's of course not finite dimensional, but it's small in the sense if you restrict to Sn, this is what I call this row Rn, it has only dimension d to the n. It only grows exponentially. In the context of permutations, that is fairly small. Because the group algebra Sn has dimension n factorial. Yeah? So that's bigger if n is large. So that means it cannot be faithful. Yeah? If n becomes large, that won't be faithful. So that is an interesting observation if you know the PhD thesis of Wassermann. Yeah? Because there is a result which characterizes which extremal traces are faithful. So he proved the following result. If you look at some extremal trace on the group C-star algebra of S infinity, parameterized by Thomas parameters, it's faithful if and only if one of two situations appears, namely either the sum of all parameters is strictly less than 1. Remember, it can be anything from 0 to 1. So if it's strictly less, you have faithfulness. Or if you have infinitely many parameters that are not 0, certainly not in the examples I wrote down so far. Yeah. And if that's not the case, it's not faithful. Yeah? Okay, so we conclude. Our characters are not faithful, so that means our parameters must sum to 1, and there are only finitely many. But there's no limit on the number. Yeah? Okay, that's already some extra information that we got, but it's not all. Yeah, we need more. Yeah. One example maybe of a character that is not Yang-Baxter. Yeah? A very extreme case is if you take all parameters to be 0. Yeah? That's a possibility. And, well, Thomas' formula tells you any n cycle is evaluated to 0, except the one cycle, which is evaluated to 1. So that's a Plancherel trace. It's not Yang-Baxter, it's too big. Yeah? Yeah, so group for Neumann algebra is too big. We always have, we really lose something in the representation. Okay, so that is one thing, but it's not all. And we are now venturing into subfactor territory. Yeah? Something, well, I would say three of us are not really experts in, but we were learning a little bit with this project in mind, because it's the right tool to answer these questions. Yeah? Okay, so I call something a Yang-Baxter subfactor, and I should now talk a little bit about von Neumann algebras here. So one thing is certainly anticipated already. I looked at this infinite tensor product earlier, just defined algebraically, but now I weakly close in the trace. Yeah? So the trace is faithful and normal on this algebra. So I suppress the G and S representation because you don't have a kernel here. Yeah? So I just close it in this trace. That is what I always call curly E, reminds me of endomorphisms. Yeah? It's a fairly big algebra, type 2-1 factor. Yeah? And I look at a subfactor. The most natural thing to do is, well, I now take my Yang-Baxter representation of the group and the von Neumann algebra generated. So I said, any Yang-Baxter character is extremal. That means this is a factor. Yeah? Or in other words, it's just the von Neumann algebra containing all generators, yeah? All represented generators. Yeah? So this is a factor, and it's always 2-1 unless R, well, if R is the identity, it's of course just trivial, or if R is minus the identity also, but in all other cases it's 2-1. Yeah? So you have a subfactor 2-1 in 2-1. Yeah? And that should tell us something about our R. Yeah? It turned out that is not quite enough. You want to look at something in addition, another subfactor, coming from a subgroup. And this subgroup, which I call here S infinity or larger or something, is simply the subgroup of all permutations that fix the first element. Right? It's a subgroup isomorphic to the full group. Everything is just shifted one step. And, well, if you have a subgroup, you can, of course, construct another von Neumann algebra, another, which I call now N, and I see I'm in line with the notation of all the talks. Yeah? So it's N and M. It seems to work out. Just the von Neumann algebra generated by the subgroup representation, or in other words, you drop the first generator sitting in M. Yeah? So that is what you have here. That knows quite a lot about R, it turns out. Yeah? Yes, I should now quote some literature. Because independent of the Yang-Baxter equation, such subfactors have been investigated by various people. For example, I should mention in particular the work of Gohm and Köstler in various papers that I will refer to also later, which was very essential for us, and also of Makoto Yamashita. Both of these parties proved independently when is this subfactor irreducible. Yeah? So you can characterize, and the answer is simple. It's irreducible only if you're in these four cases I wrote down. Yeah? If and only if. Yeah? Yes, I should maybe mention as an aside, you can also look at this subfactor M in E. Well, that you cannot expect to be irreducible. For example, if R is the identity, you just have complex numbers in E. That is really quite a big difference. Yeah? But if R is a flip, it's irreducible. That is also a result of Wassermann. But in general, not. In general, not. It's much bigger in general. Yeah? Okay, so we have this relative commutant, and there is something interesting sitting in there. It's not just complex numbers, at least if we forget about these four special cases. Right. Yeah, I have a picture here. I have to remember what. Yes, I remember what I wanted to say. Yeah? So I want to compare the subfactor N and M with something more concrete. Because, well, maybe I should. Well, I will have a picture soon enough. I have the subfactor N and M from the subgroup, and you can talk about it independently of R-matrices. you can analyze the relative commutant, for example, or the index. It's finite index. I don't know the value, but yes. And can talk about all kinds of properties, but it doesn't tell you much about the R-matrix. The R-matrix really lives in this tensor product language, and you have to combine, you have to connect to that word. Yeah? So if you have this, let me draw just a picture. Yeah? So S infinity permutes all your numbers. S larger infinity keeps the first one fixed and permutes something, well, starting from 2. And what I want to compare to, well, is our full von Neumann factor E, which has just the endomorphisms in every slot, right? And I compared with the one which keeps the first fix. Looks fairly similar, right? Yeah, so this clearly is also a subfactor. Yeah? So that is the situation we are considering. It's more explicit. We will be able to extract much more explicit information about the R-matrix from this setting. Yeah? So that's now the story. We compare, on the abstract side, let's say, these two subfactors, which comes from the subgroup n in n, and in particular the relative commutant in n. That's what we want to look at. And the comparison with the concrete setting is, well, n is, plays the role of identity and then all the endomorphisms. And the relative commutant, I just write end v, which acts only in the first factor and trivially in all the others. Right? So that's the other level. Yeah? So these are, this is the other level. Yeah, so I'm here in a situation where I have subvectors with a trace, and I always have these conditional expectations. Yeah? The trace preserving ones. And the conditional expectation here is very simple. That's good because it's so explicit. Yeah? The physicists call it the partial trace. Yeah? So let me write that down, and I apologize for having too many e's around. Yeah? But what can you do? Yeah? So conditional expectations apparently must be called e, and endomorphisms also somehow. Okay, let me try to get that straight. So straight e is the conditional expectation of this huge infinite tensor product onto just the first factor. Yeah? And what is it? Well, simple enough. You take the trace in every copy, and the first you leave alone. Yeah? That's called a partial trace. So maybe I wanted to draw maybe a picture or so. Did I? Yes. Yeah, so you have some guy, some big tensor in your von Neumann algebra here, and that is 1, 2, 3, 4, 5. And now taking the partial traces means you connect it up like that, and you leave this alone, and you have just an operator in one factor. Now that's a partial trace. And that is the conditional expectation of that inclusion. So that we have at our disposal, and we can do it concretely for R, for example. Also, the first subfactor, which comes from the subgroup inclusion and the relative commutant in this representation, has also a conditional expectation, of course, but it's not so explicit. It's there, it's unique, and how would you get it? Well, I draw a picture again. I wrote it's given by averaging over larger subgroups. So what I mean here is, so I have all my integers, and my subgroup is infinity larger, it sits here, right? And I could, well, say I make an S infinity larger up to some number n only, a finite group, which keeps the first invariant and then does something from number 2 to n. So I can average over that. It's a finite group, easy enough. And what I want to do is I want to average over larger and larger subgroups so that I end up in the commutant. Yeah? I want to end up in the commutant of that guy. Yeah? So I have to take averages over that and limit to infinity. That goes to the conditional expectation. Yeah? In the right, it's in Tuno. Yeah? Okay. So that is what you have. Or in a picture, in the somewhat incomplete diagram picture, here, down there, you have this conditional expectation ER, which, as I explained, is the limit of averaging over larger and larger finite subgroups. Here you have the partial trace. Here you obviously have an inclusion. Here, it's maybe not entirely obvious. Yeah? In the end, it turns out you do have an inclusion and you have a commuting square, but it's not so obvious from the beginning. And the key step to do that is you have to understand what happens to the first generator, this guy R1, that exchanges number 1 and 2. Yeah, so you have to compare these two conditional expectations on R1. Well, and what you can do, I mean, the partial trace is easy to take, and the limit is doable. And well, let me first give you the result, which is it's the same. Yeah? But it comes with a twist. Yeah? So you don't get it completely straightforwardly. So when you compute that, one side is straightforward to compute, the other is this limit, you get something funny. Yeah? You see it's the same if and only if you have the following diagrammatic equation, or I mean it as an equivalence. So this is supposed to be an R matrix. So an R matrix has 2 upper and 2 lower legs. And if I do partial traces, I have a choice. I can take a partial trace on the right, and I can take a partial trace on the left. It's not the same in general. I mean, for general operators between tensor squares, that makes a difference. Yeah? But when you do that proof, you see that's what you need. Yeah? And you have to fiddle around a little bit with it, and then in the end you can show this is actually the case. Yeah? It doesn't matter if you take the left or right partial trace, and that is an important step here. Yeah?
So this follows from the equation, right?
Well, in a hidden way, it's far from. So I mean, I will come to that in more detail. So this is similarity of matrices. Yeah? But I will come to it in more detail. It is not obvious to me at all why it should be that way from the outset. Yeah? Once you have that, you are in a very good situation because you can rely on Rolf's work here together with Klaus, and they work in a big framework of non-commutative probability, and they have their own version of Thomas theorems just in terms of conditional expectations. And that is somehow the key link you need to have to link up with their work. Yeah? And if you have that, you have the following result, which is very good for us, yeah? Which tells you the following. First in formulas, then in pictures. So in formulas, you take an n cycle, well, at least 2, and you get an alternative formula for the character. Namely, what you need to do, you take the representer of the first switch, go to the partial trace, take it to power n minus 1, and then take the trace. I should draw a picture. Then you see that it is somehow a striking thing, and maybe one can also see why it is so helpful. Yeah? So the left-hand side is, say, if we had a 4 cycle. If you write that down in terms of boxes, so this is R1 times R2 times R3, and you need to take the trace of that. So that goes as follows. Yeah, you link it up in this fashion. That's the left-hand side, right? And the right-hand side is you take the partial trace, to power 3 and link it up like that. And that's the same, yeah? For all n. And once you have that, well, you are in a good situation. Yeah? So it simplifies the whole story quite a bit. Yeah? And well, I can't really go into the proof. There are various elements to it. So this expectation onto the relative commutant is a fixed point algebra under some endomorphism. Yeah? And you can use some kind of ergodic theorem and push certain generators out to infinity, yeah, where they factorize off. And that is, very roughly speaking, what's happening here. Yeah? So that's the main idea how to prove that. Yeah? Okay, so that's a nice theorem, and it has first good consequence. Namely, we can now completely understand this equivalence relation very easily. I prefer now to switch to the not normalized usual partial trace, which I call PTR, which is just the same as a partial trace but not divided by dimension. Yeah? So it's just a normal partial trace, right? And if you take that, well, this formula you just write as the trace of a power of the partial trace normalized. And if you look at that formula, well, suppose, well, I'm claiming R is equivalent if and only if the partial traces are similar. Suppose the partial traces are similar, well, then they have the same traces, of course, and the same dimension, so, well, you have the same character. Yeah? And if you have equivalence, well, then you have the same character and the same dimension, so you must have all powers of the partial traces must have the same trace, and that's enough to conclude similarity. So to check, given two R matrices, are they equivalent or not, you just need to compute the partial trace. Yeah? It's very easy. Yeah? So you don't need to compute these infinitely many higher traces.
So I've forgotten.
Yep.
Oh, it has this product property with this joint product. Okay.
Yeah? All right. Yeah. So maybe to really drive home the point that it is easy, an example in 2 dimensions. Yeah? If you have 2 dimensions, your R matrix is 4 by 4 because it's on the tensor square. Yeah? So it's something like that. Yeah? So how to compute the partial trace? Well, you split it up like that, and you take the trace blockwise. That's the partial trace. Yeah? So all you need to do is look at that matrix, compute the eigenvalues and multiplicities. Yeah? So the spectrum of the partial trace determines the equivalence class, and that reminds us a little bit of this work of Okonkov, who also has spectral characterization of such representations. The precise connection is unclear at the moment, but spectral data appears. The spectrum of R alone is almost trivial. It doesn't tell you anything, but the spectrum of the partial trace is quite interesting. Yeah? It has all the information you want. Good. When did I actually start? Like
7 minutes later.
well, that is, I have like 10, huh? Okay.
You have 15.
That is even better, because I don't want to rush too much. I want to now draw another conclusion, yeah? Because I told you Yang-Baxter characters have more properties than written down here for general extremal characters. Yeah? For example, you have identity here, and you only have finitely many. But there's one thing more, yeah? And that I now also want to conclude. And I write down this master formula here, yeah? Where I express the trace on an n cycle as the trace of a power, and I write it down in parameters. The left-hand side is simply Thomas' formula, and the right-hand side is I just write the trace in terms of the eigenvalues of the partial trace. So from that equation, you get a lot. Namely, you get that these parameters, well, I should maybe make a little calculation that convinces people best. Yeah? I make a very simple calculation where I pretend there would be no sums and no multiplicities. Yeah? So I just look at the equation of this form. On the left, I have something with power n. Here I have some d to the minus n. And here, and that is the essential bit, I have something with power n minus 1. That is the only thing that is really important here. Yeah? So that is somewhat, it's a caricature of this equation. Yeah? The sums won't matter very much. So what do I learn from that? And that holds for every n, right? So I divide by x to the n, little calculation here. So I have d x y to the n, and there's one guy like missing. Yeah?
Gandalf,
Yes.
your calculation is being hid by the laptop screen.
That is very unfortunate. Thanks for pointing it out. I calculate again here. I hopefully get the same result. So I had an equation x to the n is d to the minus n times y to the n minus 1, and I was putting it in this form, dxy to the power n times 1 over y. So I take for all n, right? So I take limit n to infinity. Either this blows up, well, then it's not true. Or it goes to 0, well, then it's also not true. So y is d times x. Yeah? So I get y is d times x, and y is 1. Yeah? And you can do something very similar if you have sums, and your conclusion is the parameters are rational. Yeah? So if you include multiplicities, you find they are rational. So that is the last extra property that we can extract here from the subfactor setting on the Thoma parameters of Yang-Baxter characters. Yeah? They sum to 1, they're only finitely many, and they are rational. If you put the right topology, sorry?
Are the TJs also rational automatically, or?
They will be much nicer than that. I'll come to that, yes. Much nicer. In particular rational, yes. So that is like the Y here, the TJ. Yeah? So if you put the right topologies, it's even a dense then subset of this Thoma simplex. So in a vague sense, all characters are approximately Yang-Baxter. Yeah? But okay, that is more hand-wavy. Okay, summarizing for this bit, what have we learned? Two main things. Two R-matrices are equivalent if and only if they have similar partial traces. That's a nice characterization, but it doesn't tell you what all the solutions are, right? It's just a tool to distinguish solutions. And you learned if you have the Thoma parameters of a Yang-Baxter character, well, this lies in some subset which I call TYB, and it has these three extra properties. Only finitely many, sum is one, all rational. Yeah? Go. Now, I want to convince you for all these parameters there is also a solution. Yeah? So it's really one-to-one. Yeah? So I want to go the other way. And that, I can't see that subfactors help me very much. I need to be constructive. Yeah? I need to write down R-matrices in some sense. Yeah? Yes, and if you think about it a little bit, so it's a bit like well, decomposing group representations or summing them up with direct sums. Yeah? So we have some very simple ones like plus minus 1 and the flip, yeah? And we want to compose them to more interesting solutions. So if these were just representations of some finite group, or well, I would just take direct sums. Yeah? But, well, I should point out, well, so our representations are type 2, yeah? So they are reducible. Yeah? So they are very much, they have a huge commutant. And also if you restrict to fixed n, they are still reducible. Yeah? So forget about taking direct sums. Yeah? Direct sums don't even work anyways, because we work with tensor squares. Yeah? So we need a replacement for the direct sum that works with Yang-Baxter. That is somehow the essential step here. And if that's the direct sum, well, I should maybe make a picture again. So direct sum goes like that. Yeah? So we want to do something similar but different, and for that I had to learn some Japanese or Chinese. Yeah? And now I have to do this right, because if you write such a kanji, you have to do it in the right order, I learned. Yeah? So there are many Japanese and Chinese in the audience, so judge me. Yeah? It goes like this. Yeah? I guess, yeah? Very good. And apparently I was informed it means rice field, so you can have a little snack now, yeah? But that will be the operation we need to define, which works nicely for constructing R matrices. Yeah? So that's the symbol. It's a bit like a direct sum, but not quite. And the setting is easy, yeah? You just take two Hilbert spaces. Could actually be infinite dimensional at this point, so then I should write bounded here. And you take two operators on squares. Yeah? You take x on the tensor square of one and y on the tensor square of the other. And now the box sum is supposed to be an operator of the square of the direct sum. That's what you want. Yeah? And maybe I first tell you in formulas, because in formulas that's terribly simple. If you expand that out, well, you have different tensors. You have v times v. Well, there you use x. Yeah? You have w times w, well, there you use y. And then you have the mixed ones, there you use a flip. Yeah, so that's the definition. Yeah, you can write it down here as a formula. We found it, or well, let's say versions of it in old work by Lyubashenko, for example, Gurevich, Hitarinta. There are variations are possible, but they are all equivalent in our sense. Yeah? So that is very simple, and well, my chairman told me I have a little bit of time, so do I do a calculation? No, maybe in a second. Yeah. So let me first summarize some straightforward properties of that operation. Yeah? Commutative, associative. Interesting for us, it preserves the Yang-Baxter equation. You take two solutions, you add them up in this funny way, it's still a solution. That is interesting, and it's not hard to prove, but important, of course. And we saw partial traces are important, so the partial trace of this box sum is just the usual direct sum of partial traces, just because the flip has no partial trace, it has zero partial trace. So these are the properties that we will really need, and we can now go ahead and build R matrices from simple blocks just by summing up. So an example, take V and W complex numbers, easy enough, and here your first operator is 1. The second operator is also 1. then this guy, no, I messed it up actually. But this guy is a 4 by 4 matrix, yeah? Because you have 1 plus 1 squared, so it must be a 4 by 4 matrix. Yeah? So, and how does it work? Well, you have one direction where this tells you what to do, let's say here. One direction where this tells you what to do here, and on the rest you flip. Yeah? So it's a flip. Yeah? 1 plus 1 is not 2, it's a flip. Yeah? Okay, so like that you can work that out. And more generally, well, you just take sums of several. So what you do here, you pick any integers which somehow play the role of dimensions, yeah, and you add up many plus and minus signs. Yeah? So when I write 1D, that is a d squared times d squared matrix. Yeah? And you sum it up like that. Yeah? That is our what we call a normal form. And the theorem is the Thoma parameters of this normal form you can directly compute from these dimensions. Namely, you just divide by the overall dimension of this guy at the end. Yeah? So that's the formula. And, well, if you look at it, you can write any such rational stuff summing up to 1 exactly in this form. Yeah? So that tells you you have a one-to-one correspondence between the subset of the Thoma simplex and Yang-Baxter characters. Yeah? That works exactly out with such normal forms. Yeah? Okay, I should probably come almost to an end. There is one nice twist to the story. Now that we know rationality, it's better to switch to rescale parameters, where I multiply the parameters by the dimension. Yeah? So these will be integers, and it relates back to your question. These integers are just the eigenvalues of the partial trace. Well, forgetting signs. Yeah? So the partial trace will never have eigenvalue 0. It will have eigenvalues somewhere in plus minus 1, plus minus 2, up to plus minus dimension. And if you forget about that, about the signs, you get these parameters. Yeah? They sum to d. So what you have here, you have a situation where you have two integer partitions. Yeah? So you have two sets of integers. Well, they sum to something, namely the dimension. And that gives you a nice way how you can parameterize all your R-matrices. Yeah? Integer partition is just the same as a Young diagram. You need two here, one for the alphas, one for the betas. So this quotient is really parameterized by pairs of Young diagrams. Yeah? So you can write it like that. The quotient is in one-to-one correspondence with ordered pairs of Young diagrams, just mapping to these parameters and reading them as partitions. An example, yeah, this you can now view as an R matrix, 3 plus 1. So first you count the boxes, it's 8. Yeah? So for alpha, you look at the left guy, it's 3 over 8 for the first, 1 over 8 for the second, and then you get quarters here, yeah, for the beta. So you can directly read that off, and that is one-to-one. Yeah? So every ordered pair of Young diagrams is an R matrix. I should probably almost come to an end, I suppose. I skipped something. I told you this R0 is not a ring, but almost. It has the sum operation. It also has a tensor product, and they play nicely together. Yeah? So it's a semi-ring. Yeah? So I skipped that. I very quickly just sketch one thing, namely, if you now look at the representation as such, and here I have the Yang diagram, which also labels the irreducibles of Sn, yeah? Up to 1, 2, 3, 4, 5, 6 here. You can wonder how to extract the multiplicities from such an R matrix. Yeah? There will be certain numbers on there. And at least, well, you can now compute by a combinatorial formula with sure functions and things like that. Yeah? But one thing is more striking, which you can explain very easily. You look at a box, B of R, which just cares about the number of non-vanishing parameters, 1 plus number of non-vanishing alpha times 1 plus non-vanishing beta. So for example, for this guy, you have such a box. And then the result is you have multiplicity 0 if the box fits inside the diagram. This, by the way, is a temporally leap type solution. Also, temporally leap with parameter 2, we can completely classify now in rank and dimension. Well, if you take this particular guy here in dimension 3, rank 2, well, it looks like that. Yeah? So a lot is gone from the diagram. And okay, I'm out of time, so I wrap up by basically two challenging questions that are on our agenda. Namely, first of all, I want a spectral parameter around, which hasn't appeared at all, so somehow Baxterized maybe. That would have a direct impact on quantum field theory. And a different direction would be drop the assumption R squared is 1, which admittedly takes away many of our tools. But there's something in the work of Gorham and Kessler, again, also about braidable sequences versus exchangeable ones, so something might be saved, who knows, that would connect to representations of braid groups. With that, I conclude. Thanks a lot.
Thank you, Gandalf, for this beautiful talk.
So isn't the spectral parameter trivial? Just use it.
You can view it like having spectral parameter 0. Yeah, so you
You can just put one in. There's one that works for the ordinary thing. Because it all depends on the relations in the symmetric group. There's three.
no, but I mean, well, you could say it's a constant solution. If you view it as a function of spectral parameter, it just doesn't depend. Yeah.
There's one that just works for in the group algebra of S3.
But a constant one, I mean, you get sums and stuff, yeah? So in the Yang-Baxter equation, yeah? So you start with parameter A and B, and then you need the sum. So you can't have dependence.
So you take it, your R plus X times R plus Y times the identity. It will always work.
X times R plus Y times the other, well, certainly nothing I checked. So that would be an involution still?
It would be, oh, not an involution.
Yeah, okay.
Oh, you want an involution of the spectrum? No.
That is what you typically have for scattering matrices. Yeah? Yeah? So that is just because the inverse is given by negative spectral parameter. Yeah? So in that sense, that is what you would typically have, yeah? In the field theory setting. Yeah?
So two points. First of all, the construction of those representations of S infinity, there is a parallel. There is an embedding of S infinity in U infinity, and those the characters of U infinity were worked out by Stratilla and Voiculescu, and that there's a Springer lecture notes, and then some subsequent papers. Voiculescu. And I think I have this memory that I was going to say Piku. Voiculescu had for the parameters in the unitary case. I can't remember whether I did the symmetric group case. He had a kind of bosonic fermionic construction of obtaining those characters in the U infinity case by a sort of probabilistic thing, but with fermionic CAR CCR algebras. So that might be something to go back and look at. And secondly, when the classification of ergodic actions of compact groups was reduced by Magnus Landstedt and myself to a kind of symmetric Yang-Baxter like this. And it would appear that you probably could, if this is that classification might feed into that particular classification there, which is what were called full multiplicity ergodic actions, they're kind of bi-characters in this dual setting.
Okay.
The last thing was that in some of those early papers where these Jones-Wasserman or sometimes Wasserman subfactors were constructed for groups, so fixed points of groups with a shift, a relative commutant in the SUN case was computed by what could be written down as a diagrammatic thing, which had the same figures as say, sort of Jones projections and crossings, but of course in the symmetric case where it wasn't braided. And it would seem that in your examples, that would provide a graphical model of the higher relative commutants and all that you would get from it. That would seem to be fitting completely. Are those just remarks? But
thanks, lots to follow up on, I would say. Yeah.
The Voiculescu thing, I just do remember that Voiculescu boson fermion thing, which is a bit vaguely probabilistic, that he had in his paper as perhaps not the Springer lecture notes, but I think there was a later, shorter paper by him on his own.
No, I'd be glad to see a reference. Yeah, thanks. Yeah.
One other remark there is that there's also realization of the Thoma parameters by Virchik and Kirov. They keep the the permutation is to be flips, but they change the states. They don't have traces anymore, but
Yes,
so is there some transformation between your thing and
I can only, because of lack of time, write one formula. So, so how can you also realize the parameter chi r? You can realize it in a different fashion. Yeah? So I wrote it as a trace after the representation, right? And what you can also do is you take the representation, well, the flip, and you need some signs. So flip plus minus flip, and then you follow by a product state. Yeah? And the product state is given with a weight. And I have to be sketchy here, so the weight is A plus B, two density matrices, that is the alphas as eigenvalues, that has the betas. So that fits exactly together. Yeah?
Okay, thank you again, Jan.